Welcome friends in the next session of MOOCs on computer vision. In this session, we'll discuss camera geometry fundamentals. We'll see various definitions and terminologies used in the camera geometry like reflection, refraction, multimedia reflection, etc. We'll also see how a typical lens is made up of, what is its construction, and what are the fundamental definitions involved in the camera geometry. So let's start with the session. So let's understand the basic concepts of geometric optics. There are two main concepts called reflection and refraction. Reflection is the concept when the light ray incidents on a surface and it is reflected by a surface. And the refraction is a phenomenon where the entered light, it passes through the medium and goes through the medium. The law of Snell's follows throughout this process is n1 sin alpha 1 equal to n2 sin alpha 2, where n1 is the refractive index of the air or medium 1, while n2 is the refractive index of the medium through which light is traveling or entering. Alpha 1 is the angle made by normal towards the incident ray, while alpha 2 is the angle made by the normal while the ray is traveling through a medium. The vector representation for reflection and refractions are shown in this slide at the bottom. When light enters from one medium to another medium, we follow the principles of multimedia refraction. The law of Snell's then now becomes n1 sin alpha 1 equal to n3 sin alpha 3, where the medium 1 is the one when the light enters into light, medium 2 is the medium through which light is traveling, and the alpha is the angle made by the ray, while the medium 3 is light gets exit and the angle made is alpha. When the light is traveling from medium 1 into the medium 2 and in turn into the medium 3, some parallel shift is observed. So the parallel shift in this optical path due to the traveling path is given by d is equal to capital D tan alpha 2, where small d is the parallel shift while capital D is a distance through which light is traveling via medium 2. There is one more concept that is used in camera geometry is called as paraxial optics. When the light travels through a lens, then many a times the rays are traveling along the axis of the lens, or especially it is called as along the optical axis or z axis. When light travels along the axis which is parallel to the axis, and the angle made by the ray is very negligible or very small. So for small angle approximation, sin theta is theta, and therefore the law of Snell's becomes from n1 sin alpha 1 equal to n2 sin alpha 2, it converts to n1 alpha 1 equal to n2 alpha 2, and that is the equation that we use for small angle approximation. So whenever the incident light makes a smaller angle with the z direction or with the optical axis, then the equation turns into n1 alpha 1 equal to n2 alpha 2. While this approximation is followed to simplify the calculations, some relative angular error is introduced, and that is given in this chart. So x-axis is the angle alpha in radians, which is varying from 0 to 1.5, and on the y-axis we have a relative error in percentage. So as we can see, as we move from angle 0 towards the maximum side, the relative error grew on either side. So whenever you are dealing with angle little higher than 0, a small relative angular error is being introduced. Let's understand the important concept called lens. Lens is a central imaging element of a camera, and it has three main components. The first component is called optical axis. So you'll find the sketch of the lens in this photograph, and optical axis is this one. This axis is traveling exactly through the center of the lens, and hence it's called as optical axis or Z axis. So as per the previous discussion, if the incident ray travels along this optical axis, then the angle made by is very negligible, and we approximate it into n1 alpha 1 equal to n2 alpha 2 equation as mentioned. And such ray which is traveling close to the optical axis is called as paraxial ray. Second component of the lens is cardinal planes. These cardinal planes are three in number. The first plane is called as f dash. It is called as focal plane, and it is lies on the optical axis. Second cardinal plane is called as v dash, or it is also called as vertex plane. And this v dash, these are the points on the vertices of the lens. And the third cardinal plane is called as P dash. It is also called as principal plane. These principal plane points, they are the points inside or outside of the lens through which actual bending of incoming ray is happening, and that will lead to the outgoing ray. So whenever there is refraction or the bending of ray occurs, those points, those regions inside or outside of the lens are called as principal planes. Principal plane points P dash may be present inside of the lens or outside of the lens. So this way, the cardinal planes is a major element while describing the lens, and it has three components: f dash focal plane, P dash principal plane, and v dash as vertex plane. You will find in this slide that in the bottom we have P dash principal planes which are lying inside the lens at the central point. In the second image, P dash are just close to the vertex plane, while in this image, particularly P dash, they are outside of the lens. In the fourth image, you will find they are completely outside of the lens. So it is not essential that P dash should be inside. It may be present inside or it may be present outside of the lens. Now let's describe what is focal length. Focal length is a very important parameter in camera geometry, and it describes the distance between the lens and the image sensor. The lens is a filament where light actually falls, and the image sensor is present inside the camera on the surface of which actually light gets traveled and falls, and the image sensor in turn generates some charge and electric signal which is carried further. So focal length of optical system is a measure of how strongly system converges or diverges. There is some distance between lens and the image sensor. A system with a short focal length has a greater optical power, and vice versa. It bends the rays more sharply, bringing them to a focus in a shorter distance. On this slide, in the bottom picture, you will find that this is a picture which is recorded from a 28 mm lens. 28 mm is a focal length, so it's a distance between the lens and the image sensor. While if I increase the distance between lens and image sensors, I get this picture and I can see the object more clearly. I get a zooming effect. In the third picture, you can see the focal length is 70 mm, and I can still a bigger view, more detailed view of the object. And finally, the last picture, the focal length is 210, and you get all minor details on an object. So if focal length is increased, you get a very amplified view, while if the focal length is very small, you get a holistic view, and that's why it is said that system with a shorter focal length has a great optical power. Now, in continuation, there is a concept called digital zoom and optical zoom. So here is an object, and a watch has to be highlighted on a building. When digital zoom is applied, we get the clarity of image as shown over here, and when we use a optical zoom, we get a more better quality. The reason is that digital zoom is used whenever it is not possible to go closer to the object and the focal length remains same. But in optical zoom, the distance between lens and the image sensor is changed physically, and therefore you get more fine details by changing actual arrangement of the lens and the image sensors. Therefore, optical zoom give you best quality as compared to digital zoom. So friends, in this session we have learned camera geometry fundamentals. We have learned some definitions like reflection, refraction, multimedia diffraction, law of Snell's, and when the light ray passes close to parallel z-axis, then it is called as paraxial domain and the rays are called as paraxial rays. So these are some important definitions which are used while describing the camera geometry. And then we have seen very important parameters of lens, which are focal length, cardinal planes, and finally there are some important concepts related with digital zoom and optical zoom. So that's all for this session. Thank you friends. Thank you very much.